So following on from some of the earlier videos, we were trying to understand why the arc length in 3D space is given by this. And then in the previous video, we got to this stage here. Where if you take the limit as n tends to infinity, this thing here becomes this, and this thing here becomes this. And then I made a mistake in the previous video. I forgot the squared here. So I forgot this squared and I forgot this squared. So it should take you to this. And then well, f prime can be written as dx by dt, and g prime can be written as dy by dx. So this is in 2D. In 2D, the arc length is given by this. But then I hope you can accept that if you extend it to 3D, then you can append this bit right at the end. Now, most of you can, well, some of you can accept this. You can just attach this and extend it into 3D. But if you can't accept this, then well, if you can accept it, then move on to the next video. But if you can't, then try and understand why. At the moment, the arc length in 2D is given by this. In 3D, it's given by this. Everything's exactly the same, but then you add this element here. So if you look at this, let's try and understand why you can just stick this bit on right at the end. So if you look at this bit here, hang on, going back to here. So remember, for a small change in time, this height here represents this thing here. So this, you can think of this as being the distance traveled for a unit of time, and then this height here represents this thing here. So you can think of this as being the distance traveled for a small unit of time, delta t. So by using Pythagoras, you can work out the diagonal length. Now in 3D, well, if this represents a distance traveled for a unit time, and this represents a distance traveled for the same unit time, then in 3D, then you can extend it into the z direction. So going back to high school, remember a long time ago when you were in high school, you were given a box of length A, B, and C, and then you're asked to find the longest metal rod that you can fit in the box. And the way you would do that is to look at this triangle here. This thing here, the diagonal length here would be given by a squared plus c squared square root. Let's just call that w. Okay, so and then once you've got w, then you can look at this. This is b here. So now you would use this right angle triangle. So this diagonal length here, let's call it capital L. Capital L is given by this thing squared. So that would be, remember, this thing squared would be a squared plus c squared, and then you would square the b plus b squared, and then you square root the whole thing. So the longest length that the metal rod can be is given by this. So now this is the same idea. For a small change in time, you would have traveled in the x direction by this amount. For a small unit of time, you would have traveled in the y direction by this amount. Let's just imagine this as y, and then for a small change in time, you would have moved up by this amount. So the distance traveled would be this diagonal thing here. So if you go back and have a look at this, hang on. So a small change in time. So remember, this is in 2D. In 2D, a small change in time, delta t, you would have traveled by this amount. And a small change in time, you would have traveled by this amount, which is this height here. And then if you extend it to 3D, then you can have another dimension, but the total distance will be you using Pythagoras on all three dimensions. So it's the same as down here. Hang on. So you can imagine this as being a small change in time. This is like dx by dt. A small change in time, you would have moved by this amount. And then imagine this as dy by dt. So a small change in time, you would have traveled by this amount. And then a small, imagine the height as being dz by dt. So a small change in time, you would have traveled by this amount. So combining all three directions, it will give you the distance from here to here, which is really this thing here. I hope you can accept that. Okay.